Car motion, problem number 1. Here's our problem. We have a car starting from a stop sign, and it moves along a straight road, and its position as a function of time is given right over here. And that looks a little funny, right? But sometimes the AP questions are like that. They put letters in, Greek letters, in for the numbers, and later on they tell you what the numbers are, complete with their units. Okay, so alpha is 2.1 meters per second squared, and beta is 0.13 meters per second cubed. Those units seem funny, but if you multiply them by basically the time squared here and the time cubed, you wind up with meters, which is position. So we have 4 things to do here, and frequently the problems, for example, C and D, might depend on what you find in A and B. Okay, so it's important that you get those right, but if you don't for the AP exam, for example, let's say you get a wrong answer to part A and you need that answer for part C, as long as you do the work in part C correctly, you will get a correct for data. You can get full credit here even if you don't get the right answer. So what do we have to do? First, the average velocity of the car from time equals 0 to time equals 5 seconds, then some instantaneous velocities, then the time for when the car is again at rest, and you can see it starts at rest because if you plug, well, let's erase this so you can see it, time equal to 0 into this equation, you get the position is equal to 0. And then we want to find out how from the starting point will the car be at rest again. We'll start with letter A, and we've taken the whole problem and boiled it down to this statement right here. And our first thing is to calculate the average velocity from t equals 0 to t equals 5 seconds. The very next thing we'll do is get rid of that awkward alpha and beta and all these units here. We don't really need them to solve the problem. So we'll substitute the values in, and we have position is 2.1 t squared minus 0.13 t cubed. And we're not going to worry about the units. Clearly units are very important. However, when we start doing the algebra like this, we're going to assume we get the units right and just focus on the functions. Now there's 2 equations that can be used to solve for average velocity. We have the definition of average velocity here, which is delta x over delta t. And here's what we can find by averaging your initial and final velocity. Which one is appropriate here? We know that this equation here can only be used when acceleration is constant. So how can we find out if the acceleration is constant? Well, we can take the second derivative of the position function. Okay, what you will get will be the acceleration is 4.2 minus 0.78 t. Notice it is a function of time. That means the acceleration will change with time, so it will not be constant. So we cannot use this equation. We have to use this one. Now that we have our equation, we will evaluate the position equation at t equals 5 and t equals 5 seconds. That's what we have here, and we find that x of 5 is 36.3 meters and x of 0 is 0. We only have 2 significant figures here in the problem, so our answer is limited to 2 sig figs. But since we have an intermediate step here, we'll carry an extra significant figure. We now substitute those 2 values into the average velocity equation. X of 5 minus x of 0 divided by the time, and we get 7.3 meters per second, and note that the final answer has the correct number of significant figures. Calculate the instantaneous velocity of the car at 3 points. Instantaneous velocity requires a derivative. The derivative of the position is going to equal 4.2 t minus 0.39 t squared. Right, the 2 here comes down, multiplies 2.1, you get 4.2. Subtract 1 in the exponent, you get t. And the right here, the 3 times 0.13, 0.39, and take 1 away from the exponent, t squared. Now it's just a question of subbing in t equals 0, t equals 5, and t equals 10. That was down here. And here's our answers for the instantaneous velocities at those different times. Calculate the time it takes for the car to be again at rest. How do we find velocity? We take the first derivative of the position, and that will give us velocity as a function of time. If we want it to be at rest, that means the velocity has to be 0. So here's our derivative. There's v of t. We set that equal to 0. And note, we have two solutions here. We factor out a t. We have t equals 0, and t will also equal 11 seconds when we do the little math down here. Here's our other solution, 11 seconds. Now, we're asked for the time it's at rest again. So t equals 0, right? And let's see this little t here. Either that's equal to 0 or this is equal to 0. So where t is equal to 0, that's where we began the problem. But that's not what we're asking. We want to find where you get to 0 again. So we will use the 11 seconds. And as we said earlier, you don't see any units anywhere in there, but we know what this has to be. Time is in seconds, and we'll add it to the end. And also, our answer will be in 2 sig figs here, but we're going to use this for part D, because it's going to require that data point. How far from the starting point will the car be at rest? Here we're going to use an answer we got in part C, where we found the time that it would be at rest again. And that time was 10.8 seconds to 3 sig figs there. So here's our equation for position. The time at rest is when t is equal to 10.8. So we go ahead and substitute that in, and we come up with 81 meters.